All right, here we go. So we're going to learn properties of logarithms today, 4.2. So let's talk about some common logs and natural logs. A commonly used base of logarithms is base 10. Logarithms of base 10 are referred to as a common logarithm. Okay, and we usually leave off the base when writing these. So let's remember, you won't see it with log base 10 of x. You'll just see log x, and you have to automatically remember that that's base 10. Okay, so example 1. The state of Utah has one of the fastest growing populations in the country with an annual growth rate of about 2%. The number of years it takes for a population with the growth rate of R to double in size is this. So it gives us our equation for us. At the current rate, how many years will it take for the population of Utah to double in size? Well, when we do this out, remember our rate is 2%. Now, before we plug that in though, we have to change our 2% to a decimal, which is moving it over twice. And then we're able to plug in. And in our calculators, we're able to do log base 2, not base 2, log 2 over log 1 plus R. Now, last year in secondary 3 or in AP, you might have realized, hey, on my graphing calculator, I can change the bases of my log. But if you look at the calculator you're doing now, it only uses log base 10 or natural log. So luckily for us, since we have log base 10, we just have to say log of 2 divided by log of 1 plus, and of course, instead of R, we're going to put that 0.02 in there. And then we press enter, and you'll see that it is approximately 35.0028. So approximately 35 years, because we're talking about years. Okay. Don't forget that when you write your answer, since we are dealing with a situation, we want to put down our unit. Okay, second question for that. If the growth rate is reduced to 1.5, how many years will it take for that population to double in size? Well, our R now is 1.5%, which of course we need to change over to 0.15, 0.15, sorry. Common mistake, right? All right, and then we plug it into our problem, which is log 2 all over log 1 plus 0.015, and we get approximately 46.55 repeating. So if we were to round, we have to say approximately 47 years. And I guess in this case too, we might even say 46 years because it would have to go through the 35th year to be able to increase, okay? Another important base is an irrational number designated by the letter E. This number arises naturally in the study of calculus and financial transactions. The choice of the letter E is by the prolific mathematician Leonhard Euler, who popularized it. So think of this like pi. Pi is something that anytime you divide, what is it? Is it the circumference by the diameter? You will always get pi. It's a number that just reoccurs. This is the same thing with E. So the value of E is approximately 2.718, and it goes on forever. That's why it's irrational. The number of E may be defined as the value of the exponential term, 1 plus 1 over m to the m, where the value of m gets larger every step of the way. So a natural exponential is an exponential with base E, and E has to be greater than 1. We already studied the graph and the properties of the exponential function, right? So A logarithmic with base e is called a natural logarithm. Natural logarithms are used even more often than common logarithms in mathematics so that they have their own notation, okay? So when we have with base e, instead of saying log base e of x, we actually just write it as ln of x. That's the natural logarithm, okay? Now, in example 2 here, I'm going to prove to you that log base 2 of 3, which is something we cannot plug in a regular calculator, that we can get the answer to this, or that it's the same answer as saying log 3 over log 2. Now, let's remember what log 3 is. Log 3 is saying 10 to the something, and I'm going to call it m, 10 to the m equals 3. That's just me changing it into a different form, okay? Same thing is with log 2. That means 10 of something, and I'm going to change this variable to n equals 2. That's just converting, right? So the other thing is we're going to look at is, remember what this is saying is 2 to the log 3 all over log 2 equals the value of 3. So if I can manipulate this left side here and show you that it equals 3, I've proven to you that those two things equal. So let's see how I can do this. All right, we have two separate variables here. So I'm going to do some manipulation so we're down to one variable. Okay, guys? So I'm going to focus on this 10 to the n equals 2. Okay? Now, if I decided that I wanted 10 to the first, that means I would have to multiply this 10 to the n by 1 over n. Not multiply it, but set it to that exponent, okay? So whatever I do to one side, I must do to the other. And I end up getting 10 equals 2 to the 1 over n. I'm switching this around because you'll see that I'm going to manipulate this side for it working for me. And I put 2 there and it should be n. So I'm just rearranging stuff to make it helpful in a bit, okay? Now remember, I was talking about that this equals m and that this equals n, right? And that's how I converted it into exponential form. So log 3 was equal to m, log 2 is equal to n. Well, again, I'm going to manipulate this right here. So right now, I get 2 over m over n equals 3, right? Because I define that as m, define that as n. Okay, so let's take this apart. Let's go 2 to the 1 over n times m, right? Because remember, power to power, we multiply. So if I wanted to separate the power to power, I would just separate it as numerator, denominator. And that equals 3. Remember the proving that it equals 3. Now I'm going to move my work up here because I put it too small that I'm running out of room. Well, what did we just do over here at the beginning? I manipulated this, changed this all around. That I said that 2 to the 1 over n is actually the value of 10. Okay, so I'm going to substitute that in. So now I have 10 to the m equals 3. And didn't I prove that up there, 10 to the m equals 3? So 3 equals 3. And I just proved that those two things equal each other. I know that was kind of crazy. If anything, stop the video now and kind of repeat the part of proofs. Now remember, proofs are about, hey, these two equal, manipulate one side to look like the other and show that they equal each other. Okay. All right, next page. Okay, change of base property. So what I just proved to you pretty much is saying I can take any base and be able to change it into a base 10 so I can use my calculator and get approximation, okay? So let a and b be positive numbers not equal to 1, and let x be a positive number. So log base bx equals log base a to the x all over log base a to the b. Okay, that gets a little bit tricky, right? But really, what this is going to help us with is right here. If we get any base that is not 10, we can change it into log base 10 by saying log base of x all over not log base of x, log x all over log b, okay? The other thing we can do is if we want it in base E, we can say ln x all over ln b, and now we can do it in our calculator. Okay, so let's do this together. We have log base 4 of 5, and we want it in base E. So since we're doing it in base E, we're going to use ln and not log, okay? So if you remember, our b is 4, and our x value is 5. And since we're in base B, we're using the LNs. Okay, I'm just writing that down as a reminder. So that means when we have this log 4, base 4 of 5, I can simply say in our calculator ln 5 divided by ln 4. Now, I know I'm using my graphing calculator, but I promise it's just about what it looks like. On your calculator, look for the ln button. So I'm going to say ln 5 divided by ln 4, and I'm going to go out a couple decimal places, so 1.16. Okay, and we're able to approximate that using our calculator. So remember, this is converting. If we ever have to solve for a log base that is not 10, we're able actually to convert it into log base 10 to use our calculator. Okay. All right. Inverse properties. Let b be a positive number not equal to 1. So the idea, guys, is that base and log of that base will cancel each other out, just like the other way around. Log base b and base cancel each other around. So this is going to help us solve. Okay, now show that log base b equals 1 and log base b of 1 equals 0. Okay, so one thing I want you to notice is in that first one, we have log base b of b. This b is to the first. Okay, well, what did we just say up here? The log base b and the base b, since these two are the same, cancels out, leaving 1 equals 1, which is true. Okay, now if we talk about log base b of 1, well, 1 is also the value of b to the 0. Okay, right? B to the 0 is the value of 1. And now I can explain it by inverse, that this log and this base cancels. So I get 0 equals 0. So this is just showing you how you can use the inverse of them to be able to solve, okay? The other thing I want to show you is that kind of how to break this down a little bit. I know right away when you look at your rules for log, remember that coefficient out front goes to the exponent. So we can move that 5 to the exponent. Now, if you couldn't see this, to get rid of this log, oh, the base isn't there. So what is it? It's automatically 10. So I'm going to write it in. The way to get rid of that log is actually to set it to that base of 10. And remember, these cancel. Whatever you do to one side, you must do to the other. This will come into play in the next couple examples. Okay, you can only get rid of it if it's the same base, and you can only get rid of it if they're right next to each other. So see, I would have to move the 5 up before I could use the base 10 to get rid of this. Okay, so now we're going to deal with some situations that might happen to be able to solve. Now remember, if we're solving, we're saying what X makes the statement true, okay? So we're going to try to get X by itself. So I'm just going to write this in here. Okay, before we were trying to solve it to see if they could get to the same base, and we could cancel out and all that stuff with exponential. But now, as you can see, there is no way I can manipulate 2 or 3 to get to the same base. So I must use inverse of logs to be able to solve for this. So to get rid of the base 2, I actually have to use log base 2. Right, to get rid of it. But we know whatever we do on one side, we have to do to the other. Okay, now, I'm just wondering what I did here. Okay, oh, I see what they did. Okay, they did this another way too. By the way, I'm going to show you both ways right now. Okay, so of course these would cancel and we would get X equals log base 2 of 3, which we know we can't do on a calculator unless we manipulate that and change that into our log base 10. So we would have log of 3 all over log of 2. Now there is another way we could have manipulated this. If you see here, instead of using log base 2, I'm automatically going to use log base 10. So log both sides, okay? If you look, we have an exponent here, so I'm going to move that in front. So we have log x log 2 equals log 3. Now, how do you get x by itself? We divide by log 2. Now, which way, you're probably asking yourself right now, Ms. Hegman, how do I know which way to do it? If I want it that way or that way? The idea is the directions will tell you what base it wants you in, okay? So just be careful. If it wants the common base, that's base 10. If it wants you to do approximation, you're going to have to use your calculator, which is base 10. So we have to be careful. So this is a trick question right here that I want you to remember. This is another one that is a trick question. Now, what I want you to notice is here we only had one base. So we were able to use our log base 10. Or, okay, or common logarithm. But in example 7, because we have 2 different bases, okay, we're going to use ln. Okay. So as you can see right here, there's nothing we can do for a common base, so I'm going to take the ln on both sides. ln 3 negative 2x. Now what does that do? That talks about, this is our exponent. Where can that exponent go? Well, they can go out in front. So we have x plus 1 times ln of 7 equals negative 2x times ln of 3. I'm going to put parentheses so you don't think it's a multiplication. Now remember, the idea is to get x on one side. The problem is right here. We want to distribute that out, so we get x ln 7 plus ln 7, right? I don't have to put the 1 down there, equals negative 2x ln 3. All right, now what do we do? Well, let's move our x's to one side and our numbers on the other. So I'm going to have x ln 7. Now this is a negative, so how do I get it on the other side? I'm going to add it to the other side. Equals ln 7. All right, now what? Okay, don't forget here, I know the biggest part you might have wanted to do was like, hey, Ms. Heckman, why can't we just divide by negative 2x? You have to remember that that out front is an exponent. It's not the actual coefficient of multiplication. This is just how we can rearrange a natural log or logarithm with an exponent, okay? So that's why we can't divide. Now, if you remember, what we can do here now is take out an x, right? So we have x times ln 7 plus 2 ln 3 equals, oh, and this should be negative, right? Because I subtracted that to both sides. For those of you who caught it, good job. Okay, and now if we want, all we have to do is divide. So I get x equals negative ln 7 all over ln 7 plus 2 ln 3. And we're in ln's, so it makes it easier to be able to put it in our calculator. Okay. All right. Next, example 8. Show that ln 15 equals ln 3 plus ln 5. Okay. Now, usually, there's a couple ways you could do this. I mean, usually we want to say, hey, that's multiplication, right, using our properties. But we're going to use it using inverses, okay? So the last thing you want to do is do, when you do E, right, to get rid of ln, you would E both sides. But the biggest mistake people make is when they E the other side, they E these separately, and it's not. You have to E, and all of that goes in the exponent right there. Okay, you cannot do them separately. Whatever you do to one side, you do to the other. Okay, now here's the tricky part. When you add exponents, right? When you add exponents, if we were to go backwards, what is the thing you do to be able to add exponents? Well, you add exponents when you actually have a multiplication of the same base. Okay, I'm going to write this down and re-explain what I just said. Because we're used to going backwards. We're used to having something like this, and we're like, oh, it has the same base, it's multiplication, so we add the exponents, right? We're used to going that way. Example, x to the 4th times x squared equals x to the 6th. Okay, we're used to going to bringing it to one term, but in this case we're having this one term and we're separating it into two. Okay, now if you look, we have e to the ln, e to the ln, e to the ln. Those are all inverses of each other, so they cancel since they're right next to each other. And now we have 15 equals 3 times 5, and what do you know? 15 equals 15. Okay, we're just proving it right now. All right, show that log u over v equals log u minus log v. where u and v are positive numbers. Okay, so in this case, I'm going to start by manipulating one side or both sides and then go to 1, okay? So first of all, how do you get rid of the log on this side? Well, we have a base 10 of it because here we get log uv equals. Now remember, just like this side, whatever I do to one side, I do to the other, but only once. So this is base 10 of log u minus log v. Okay. The idea too is I'm proving that subtraction division property, so I can't use it, okay? In which I do use it, so, okay. So right here, those cancel and I get uv on one side. And here, I am going to use it. Subtraction means division. So 10 log base u all over log base v, right? Nope. Said this wrong. Hold on. Let me look at my work for a sec. Because subtraction would be u over v. Give me a moment. Let me train my thoughts so I don't say anything. So, come on. Sorry, guys. Okay, guys, I think I know my thought process right here, what I want now. Now, of course, we look at this as subtracting, right? But the truth is, if I have a 1 out here, and this -1 is actually in front, which I can put as an exponent, that would make this a multiplication. Okay? So, right now, think of this as log u times log v to the -1. Now, negative exponents, where can we make them positive? Well, we put them in the denominator. So right now I have log u all over log v. Now, if I do this correctly, we can actually separate it and have this being log here and log here. So, oh, and I made that u. Sorry. Okay, ready? Next step. We still have u over v on this side. That's what we're trying to get. So now I'm actually going to separate this to log, or 10 to the log u all over 10 to the log. Be careful when you guys are writing too that you want it to be an exponent, because you will get marked off for that. And then what do you know? 10 log, they cancel. We get uv equals uv. Again, these are just proving things, guys. You're not going to have to prove them. We're going to actually use the ideas. This is just saying, look, we can actually change these because later it's going to help us, okay? Same thing here. We've got u times v is that addition. U over v is that subtraction. You should remember some of those log properties from last year. All right, so now we're actually going to use them. So me proving things is just for you to be able to use them, okay? So example 10, expand the following using the properties of logarithms. Write exponents as coefficients and simplify. So exponents have to be coefficients. We need to simplify, and variables are all positive real numbers, okay? Those are your answers. You need to make sure. All right. So what happens here? Well, remember, multiplication meant what? It meant addition. So we got log base 0.1 of 10 plus log base 0.1 of x squared, right? That's what it equals. Now, the good thing is here is all we have to do is make sure that our exponents are as coefficients, so we can move this 2 out in front. And if you remember correctly, if we manipulate this on the side, that would be 0.1 to the what equals 10. And 0.1 to the what equals 10. Hold on, I don't know what's going on with my writing. For some reason they have -1 here, but hold on. Of course, guys, I'm having a brain fart right now. 0.1 is 1 over 10. Well, how do you make 10 into a fraction? That's to the negative first. So that means this is -1. And then we put that 2 out in front, and now we qualified for everything it wants us to do. Okay, just think of this as 0.1 to the negative first is 10. Okay, let me just fill that in for you guys. There we go. All right, sorry for the complication here, guys, and I'm taking longer talking, aren't I? Excuse me. All right, let's look at this right here. One thing I want to point out is log. The base really isn't there, guys, so the base is 10. Let's keep that in mind. This you have to do a lot of steps for, so don't try to do it all at once. The first thing you want to look at is that we have a cube root. So what we have here is log base 10. I'm going to write that in so we don't forget. And it's going to be 100x squared all over yz to the 5th to the 1/3. Now, of course, we're going to put the 1/3 in front, right? Because that's where our exponents go. I'm going to actually start over here so that way I use more room. So right now I have 1/3 log base 10 of 100x squared all over yz to the 5th. Okay? Now remember, we're expanding, so let's keep going. What does division mean? Division means subtraction, and multiplication means addition. So I'm going to give you a trick right now, okay? Whatever's in the numerator has an addition sign with it. Whatever's in the denominator has a subtraction sign with it. Now, if we remember, this 1/3 is out front, and it's up front for everything, okay? The also thing you have to remember is when expanding, for every term you have, you still have your log base 10, which I'm just going to put log right now. So I have log base 10 of 100, and that's positive because it's in the numerator. Then I have log plus log base 10 of x squared, because again, that's in the numerator. Then I have minus log base 10 of y minus log base 10, oops, I don't have the 10, of z to the 5th. Okay, now I'm going to bring this parentheses out closer because we still have more to go, because this is positive real numbers, exponents or coefficients, so on and so forth. Okay, now if we look here, before we distribute this 1/3 out, because we have to distribute this 1/3 out, if we look here, log base 10 of 100 is an actual number. 10 to the what is 100? It is 2. Okay, and then this 2 exponent comes in front. This is fine, and this 5 comes in front. Then we're also going to distribute that 1/3 out. So what we get is 2 times a third is 2/3 plus, now there's a 2 out front, right? Because we're moving it. 2 times a third is 2/3 log x minus 1/3 log y minus, now there's a 5 out front. 5 times 1/3 is 5/3 log z. Okay. Exponents are coefficients. Awesome. Okay. Now we're going to use the properties to condense. So we're going to make one logarithm or one ln, okay? So the first thing, remember the last thing we did was put the exponent out front. So then the first thing you're going to do is move that exponent back. So we get log x squared minus log x minus 1 cubed. And then what does subtraction mean, guys? It means division. So we have log x squared on top and x minus 1 cubed on the bottom. Remember, when we condense into a single one, there's only one. When we expand, there's multiple logs. That's going to be a little trick to remember. Okay, first, move the coefficients to the exponents. So I have ln u to the 4th minus ln 5u plus ln 1/u. Okay. Now, yes, it would be very easy for me just to put everything that has a plus sign or a positive in front of it in the numerator, and then everything that has a subtraction in the denominator. But I'm a little worried about this fraction, so I'm actually going to do this in parts. Okay, guys? So right here, this would be division. So we have ln of u to the 4th divided by 5u plus ln 1/u. Do you guys see why I did that now? Because addition means multiplication. And when I do the multiplication, I can just multiply the numerators, multiply the denominators, which gives me ln u to the 4th all over 5u squared. Now let's make sure we reduce all the way, right? Because we have to simplify. ln u to the 3rd all over 5. So we can get rid of the u. And this should be to the 2nd, right? Sorry guys, it's B-lunch. Okay, sorry, some of my work's a little off right now. So, okay, let's look at number 12 here. We have solve log of x minus log of 2 equals 1. Okay, let's think of this. We can't get rid of a log yet until it's only one log, okay? As you can see, there's 2 of them. So we have to condense it on one side. Well, what did we prove before? We said subtraction is division. So log of x over 2 equals 1. Now this is log base 10. So how do you get rid of the log base 10? We have a base of 10. All right, so these 2 cancel. We get x over 2 equals, and 10 to the 1st is 10. So x equals 20. Now, what I want you to do, and so many people forget to do this, guys, you have to check. You have to double check. So log base 20 minus log base 2. Do that in your calculator and you find yes, it equals 1. So that is your answer. Now the reason why I say that is because there are going to be some circumstances that we come out with 2 answers and one of them works and the other one does not. Hence our next example. Okay, we're going to take the same idea. Okay, so log base 2. Now addition means multiplication. Okay, how do you get rid of the log base 2? Well, base 2. So we have, those cancel. We have x times x minus 1 equals 2 to the first is 2. Okay, so I'm going to do this all out. We have x squared minus x equals 2. Let's move it on to the one side so we can factor. Equals 0. Factor that out. So we get x minus 2 times x plus 1 equals 0. So we get x equals 2 and x equals negative 1. Now we're going to plug back in and check. But of course, at this point, you should say, Ms. Heckman, what are you talking about? We can't do base 2 on our calculator without changing it into base 10. Well, let's think about some things about ln, right? Or log and ln. Let's look at the graph of our normal ln and log. What can it never be? It can never be negative, and it can never be 0. So x should never be, when you plug it in, by the way, I should say x, I don't want to say x. How do I want to say that? Let's do this value, right? When you have a log of whatever, this value right here cannot be negative and it cannot be 0. Now the reason why it can't be 0 is because that's an asymptote, remember? So if I plug in 2 here, we're good. If I plug in 2, we get 1, we're good. If I plug in negative 1, if I plug in negative 1 here, I have a negative. Plug in negative 1 here, I get a negative again. So negative 1 is not our answer. X can only be 2. So when you get 2 answers, more than likely one of them won't work. So you have to check and reason out your work. So here are some properties of logs that we went through. We can convert them into exponential. We know that log base b of 1 is 0. We know log base b of b is 1. We know that b and log, they cancel. Okay. We know that if you have a log base b on both sides, that u and v equal. Okay, we know how to change our bases so that way we can use our calculator. We know that the exponent goes in front as a coefficient. And we know that multiplication to expand it goes to addition. Division to expand it goes to subtraction. All right, let's do some practice.